Welcome back. Let's go ahead and get started with Euler's method. Now, this is probably one of the easiest methods one could possibly use for a numerical approximation. So, let me just give you an example real quick and start from there before I give you the abstract concepts, because it's really not that bad. If I have, say, dy over dx is equal to, say, just say x, just make it real easy, and the initial point is going to be, say, 1, 2. So this is x naught, and that's y naught. Now, if you think about this, what I'm saying is that you have x and you have y, and I want to start here at the point 1, and I'm going to go up 1, 2, so that's my starting point, is going to be right here. So my point is going to be called 1, 2, and I also know what the slope is. The slope is going to be equal to just f of x comma y, which is just equal to x, and that's just equal to 1. So don't forget, over here I'm writing this as saying f of x comma y is just x. And again, that's our slope. Now, if you stare at it really hard and you don't blink for a minute or two, you'll notice, hey, I have a point and a slope, I can create a line. So that's the genius of it. So you have a point and a slope. So we have the point 1, 2, and m is equal to, say, just 1 from over there. Then I'm going to have y minus y sub 1 is equal to m times x minus x sub 1. And this right here is going to be our x1, and this will be here our y1. And then you can see that we're going to have y minus 2 is equal to 1 times x minus 1. Now, here's the other brilliant thing that you can do, is if I want to go over, say, a small amount, let's say I'm going to go over here 1.1. All right, so right there, I say that my step is going to be h, which is 0.1. But remember, your step is really going to be the point where I'm going to go from, say, that's going to be just the step 1.1 minus 1, which is 0.1. So believe it or not, that distance right there is the step size. So going back over to this little guy here, as soon as I put in 1.1, so I'm going to have y is minus 2 is equal to 1, and I'm going to put in 1.1 minus 1. Minus 1. That's just our step size. Then I'm going to get that y is going to be equal to 1 times 0.1 plus 2. Now, again, if you look at this, this is basically your step size, and that is the slope that we have, right? And then this is, of course, what we have here, the point, the y value. The y value of our starting point. And that's going to tell us what we're going to get. So we're going to get 2 plus 0.1. So we get that our y value should just be 2.1. So if I come over here to my little graph, you're going to see that we're going to have a little dot right about here, about 2.1, if I go up. Okay. And remember, I mean, this may look complicated, but just remember, it's literally, look, this is just the slope-intercept point of a line, right? Just the slope point formula. That's all you need is a point and a slope. That's literally all you're doing. All right, so let's generalize this mess. So here's the general idea. So you have a differential equation, dy over dx. It's going to be some function of x and y. And you're going to have initial conditions that I will call, say, x naught, comma, y naught. Very bad with coming up with names, even in isolation. So what we're going to do, again, if you just think about this, we're going to have our point here that's going to be our x naught, and then we're going to have some y naught up here. That's going to be our point. And then our next point, x sub 1, is equal to some x naught plus some step size. So I'll usually have with a step size associated with it, or something you got to figure out. So with step size 0.1 or 0.2, etc., etc. But in this example, I'm just going to call it h. So I'm just going to call it just h. So with step size h. Okay. Now the next point in the line is going to be, so let's say we have our slope is going to be f of x naught comma y naught. That's just a number, right, which is our slope. And then we have our point, x naught comma y naught. And from that, we're going to have create a line. We're going to have L of x is equal to y naught plus the slope times x minus x sub naught. Now, if I want to know what happens at our next step size, so what happens at x1, you may ask? Well, let's put it in there and see what happens. Then the next step, the next point we have is that we're going to have L of x1 as our approximation. We're going to have L is equal to y naught plus f of x naught comma y naught times x1 minus x naught. So literally the only variable that changes in this whole mess was just from x to x point, x1. And this whole thing is just h. So to recap, what we have is, y sub 1 is going to be approximately, or I'll just define y sub 1 to be equal to the next step, y sub naught plus f of x naught comma y naught. And you hope that there's, and then times h, times this distance h. Now h is usually fixed. I should forgot to mention that, but it's usually a fixed number, so the steps don't change. So in other words, if I were to do the next point here, that one is just going to be x2 is going to be equal to x1 plus h. So you step equally sizes. Now the next one is going to be y sub 2, and I'm going to pick y sub 1 now plus f of x1 comma y sub 1 times h. So I literally just repeat, and I keep going with that. And what else is kind of cool is that we have this pattern that just keeps repeating. So let me write it out for this. So here's where we start. We start at the point x naught comma y naught. All right. Now the next one, we're going to have x1 is equal to x naught plus h. And then our comma y sub 1 is going to be equal to y naught plus f of x naught comma y sub naught times h. And then the next one is going to be x2 is equal to the previous x plus h. And the next y is going to be equal to y sub 1 plus f of x1 comma y sub 1 times h, and so forth. So at the end, we're going to get x sub n is just going to be the previous x sub n minus 1 plus h, comma, and our next y, our next y is just going to be equal to the previous y plus the slope, x n minus 1, comma, y sub n minus 1, times our step size. And this is basically what I'm going to call Euler's formula. I'll do an example, and then I'll show you the error bound for that. Now, before I go on, there's a couple things I want to mention. Note, this is rather important. The first thing is that Euler's method sucks because it's not very accurate. It does have some problems. So you're going to see that it loses accuracy with each step, and it doesn't really last for very long. But the other thing too is that Euler's method is the easiest and fastest thing to compute. So Euler's method is in fact fast and easy to use and to compute the numbers. So you may ask, well, who's going to be doing any applications of Euler's method? Well, the truth is I've actually seen some video games where they would use Euler's fluid flow, for example, these basic things, and use those models to, say, create water effects, which aren't very good. So if you'll notice that I was trying to look up some pictures for this, but then I realized I don't know if I'm really allowed to. But if you look at water, if it just has some really bad water, you know, if as water splashes, it kind of falls apart and breaks apart. And there's usually these little things called eddies, which kind of swirl around as the water moves. But if you look at a video game, usually what happens in a video game is that the water is super choppy, right? If you go back and play your old Doom games, for example, no, even way, probably like old Halo games. The first Halo game that came out, a warthog would go through, which is basically a vehicle. A vehicle would go through the water, and the water wouldn't splash or fall out or ebb or anything of that nature. It would literally just have these kind of choppy, these kind of choppy motions in the water that would make it behave like water. But of course, nobody who's playing Halo is going to stop and look at the water unless it's me and you're quarantined and you're examining the details of old video games. But you'll notice that it's super easy and fast, and that's what it's kind of used for, is very simple, easy things that you can do. And like I said, most video games, they don't really care about accuracy. I mean, nobody's going to sit there and look at water in a video game and see how it ebbs and flows and how it breaks apart and how it causes little, little whirlpools as it moves around and how your boot interacts with the water. I mean, next time you play Call of Duty and you go through water, take a good look at it before, you obviously lose because you're looking at water. But you'll notice it has very simple properties. All right, so let's finally do our example. Suppose I have a differential equation dy dx is equal to y minus x squared plus 1. And we have our initial conditions, say, we have our point as, say, y of 0 is called 0.5. And what we want to find is I'll make this a little bit more interesting. I'll say I want to find y sub 2. Now remember, right here, this is saying y sub 0 is equal to 0.5. So I'm starting at 0 and I want to end at 2. And I want to find it and say in 10 steps. Find in 10 steps. So what I'm going to do is I will say, here we have our number of steps is n is equal to 10. So then our step size. Okay, so first things first. Step 1, I'm going to say that h, which is our step size, we're going to go from start minus, or stop minus start. So it's going to be stop minus the start over the number of steps. So that's going to give us 2 over 10, which is 1/5, which is 0.2. You can use a calculator for that. That's fine. And so let's go ahead and start. We start at the point we're going to have y naught, or I should write x naught first. Whoops. So our x naught is equal to 0, and our y naught is equal to 0.5. All right. The next one is going to be x1 is going to be x naught plus h, which is just going to be 0.2. Our y sub 1 is going to be equal to, now I forgot to label this, but remember when I refer to f of xy, I'm referring to this guy right here. So this is my f of x comma y, and that's nothing more than saying our slope. So that's going to be equal to our y sub naught plus f of x naught comma y naught, that's our slope, times our step size h. So I'm going to have y sub 1 is equal to 0.5 plus f of this guy is going to be, I'm going to start with 0.5 minus 0 squared plus 1 times 0.2. Now make sure you can figure out where all this comes from. The 0.5 is the y naught. So if I go and look at my function, my y naught is 0.5, my x naught squared, which comes from over here, and then plus 1 because that's part of the formula, and then my h, of course, is 0.2. And once I figure that value out, I'm going to get, I'm typing this in. I should be using the slide rule, I know. Plus 1 times 0.2, which is equal to 0.8. Okay, so I have y sub 1 is equal to 0.8. All right, so that's the first two people. Let's try the next one. So now I'm going to have x2 is equal to x1 plus h, which is going to be 0.2 plus 0.2, which is equal to 0.4. And I'm going to write this next one, this y sub 2, in a different color so we can see it. It doesn't stick out from all this red. This one is going to turn into y sub 1 plus the slope, x1 comma y sub 1, times h. And if I fill that out, my y sub 2 is just going to be y sub 1, which is over here. So that's 0.8 plus, and I put it back into that function, 0.8 minus the x1 squared, and the x1 squared was 0.2 squared plus 1 times the h, which stays the same. In this case, it's 0.2, which should work out to be equal to 1.152. Now remember what this means. Okay, so I'm just going to say this out here. Note that this means that the function value, whatever the actual solution, so let me call the actual solution to the ODE, the ordinary differential equation that we had way back, the dy over dx is equal to f of x comma y with our initial conditions x naught comma y naught. What I'm saying is, if you look at this, I'm saying that the actual solution, and I'm going to call it y hat. I'm feeling very festive. So that's the actual solution. So the actual solution, I'm calling it y hat. What this is saying is y hat at, hey, that rhymes, y hat at this point here, 0.4, at this point, 0.4, is approximately this guy right here, this answer here. So I'm looking at these two values there. So I'm saying that the actual solution is approximately 1.152. Okay, so that's what I'm saying, is that the actual solution at 0.4 is about 1.152. Now, we haven't talked about error bounds and how bad is it, but you want to think that at every single step, because I could ask you this question and then just say, well, tell me what is approximately 0.4, or tell me what is 0.5. And you can actually just go back and look at the process. What's the x and what's the y? Now, I didn't finish this problem because it keeps going, right? It just keeps going. So you keep this process up. And what I want you to do for the test and for the homework, because it's super simple, I may make this next one and videotape it, but you want to try this on Excel, because on Excel, once you put the formula, you literally just drag it down, and then bam, all the answers come out. Now remember, you should have access to Excel everywhere, but any spreadsheet will work. So if you have Linux and you have Libra or something else, go ahead and use it. It's going to be really simple. And so on the test, I can say, what's 10 steps of this? And you really just have to do it one time correctly and then just drag it down. So next time I'll go ahead and start to show you how to do that on Excel, as well as the error bounds for this, because I haven't even begun to mention how far off Euler's method actually is.